real-time data. So these are the basic components of any discrete time system. Every discrete time system will have some adders, multipliers, or shift operators, which includes delay operators or advance operators. Now let's discuss some examples of discrete time systems where difference equation will be given to us and we will be required to find their output value or the output sample values corresponding to the given input. In this example, the input signal x of n is given to us in the functional representation, where x of n is equal to mod of n and the range of small n is from -3 to +3, and x of n is equal to 0 elsewhere. So this x of n is representing a bounded input signal where it is defined only from -3 to +3. And we are required to find the output sequence y of n corresponding to x of n when we will apply x of n on these 6 different discrete systems. So these are the 6 different equations and we have to calculate the output sequence values corresponding to the x of n sequence values. The first system is called identity system. The second system is a unit delay system. The third system is a unit advance system. The fourth system is representing a moving average system because here we are taking average of the current sample value, previous sample value and the future sample value. The fifth system is a maximum value finder which will compare the values at every instant and then provide the maximum value. And the sixth system is so-called accumulator, which is collecting all the sample values of x of n from -infinity to the current instant and then producing their summation. So the first step is we have to find the sequence of x of n because x of n was given to us in the functional form. X of n was equal to mod of n where n was equal to from -3 to +3. So when we will put -3 to +3 in mod of n, we will get 3 2 1 0 1 2 3. So in the first case where y of n is equal to x of n, which is the case of identity system, y of n sequence will be exactly equal to the x of n sequence. In the second example, which is about the unit delay system, we have to apply a unit delay operation on this x of n in order to get the y of n. So the output of a unit delay system will be equal to x of n but having a one delay introduced in it. So as you can see here, the origin was at the 0 sample value and after passing it through a unit delay system, now we are getting y of n sequence values where origin is present at 1 sample value. Similarly, when this x of n will be passed through a unit advance system, the y of n sequence will be equal to this one, where this origin or reference point has been shifted towards right by 1 sample. Now let's come to the moving average system, in which we have to add the respective values of x of n plus 1, x of n and x of n minus 1. So this is x of n and this is x of n plus 1 and x of n minus 1. And during addition we have to add the sample values present at the respective index values. So we will add the sample values present at 0 index values together. Similarly, the sample values present at 2 index value will be added together. So here at 0 index, the sample value is 1 and here the sample value is 0 and here the sample value is 1. So 1 plus 0, 1, 1 plus 1 is 2. So the answer of summation will be 2 at 0 index. Similarly, at 1 index, the sample value is 2. Here the sample value is 1 and here the sample value is 0. So 1 plus 2 is 3 at 1 index. Similarly, at 2 index, the sample value is 3. Here the sample value is 2 and here the sample value is 1. So 1 plus 2 is 3 and 3 plus 3 is 6. So the answer of summation will be equal to 6 corresponding to 2 index. Now you can write all the remaining values in a very similar way. Let's take an example of -3 index. Here the -3 index, the sample value is 2. Here the sample value is 3 and here the sample value is not present at -3 index. So 3 plus 2 will be equal to 5 at -3 index. Now after adding all the respective values, we have to divide these summation values or the results of summation by 3 in order to get the result of moving average system. So divide all the values by 3 in order to get the sequence y of n. So after dividing by 3, we will get these values, which will be considered as the output of the moving average system. 1, 5 over 3, 2, 1, 2 over 3, 1, 2, 5 over 3, 1. Another possible way to calculate the output of moving average system is that we can put various values of small n in order to calculate y of n. So here we have put n is equal to minus 4, minus 3, minus 2 and so on up to plus 4. So when we will put minus 4 in this difference equation, then it will become y of minus 4 equal to 1 over 3. Now we have to put small n is equal to minus 4 everywhere. So 1 minus 4 will be minus 3, n is equal to minus 4, and minus 4 minus 1 will be minus 5. So x of minus 3 means the sample value of x of n present at minus 3 index. So here the sample value is equal to 3 at minus 3 index, so x of minus 3 will be equal to 3. And x of minus 4, the sample value defined at minus 4 index is 0 because it is not present. So you will simply write 0 in place of x of minus 4. Similarly, x of minus 5 is also 0. So here you will write 0. So 3 plus 0 plus 0 is 3, and 3 divided by 3 will be equal to 1. So this will be the y of n sequence value at minus 4 index. Similarly, for y of minus 3, you have to put minus 3 everywhere in this difference equation. So y of minus 3 will be equal to the average of x of minus 2, x of minus 3 and x of minus 4. So here as you can see, x of minus 2 is equal to 2. So you will write 2 here, and x of minus 3 is equal to 3. So here we will write 3, and x of minus 4 is 0. So 2 plus 3 plus 0 will be 5, and 5 divided by 3 will be 5 over 3. Similarly, you can calculate all the remaining outputs. For example, y of 3, for the calculation of y of 3, we have to put small n is equal to 3 in this difference equation. So it will become x of 4, it will become x of 3, it will become x of 2. So after adding x of 4, x of 3 and x of 2, we will divide by 3. So x of 4 is 0 because it is not present here. X of 3 is equal to 3. So here we will write 3, and x of 2 is equal to 2. So here we will write 2. So 3 plus 2 is 5, and 5 divided by 3 is 5 over 3. Now let's come to this example where we have to find the maximum value present at the respective indices in these three sequences. So in each case we have to compare values at respective indices, and then we will find the maximum value. So here the sample value present at 0 index is 0, here the sample value is 1, and here the sample value is 1. So when we will compare these sample values present at 0 index value, the maximum value will be 1. So at 0 index the answer will be equal to 1. Now at plus 1 index the sample value is 1 in x of n. Here the sample value is 0 at 1 index, and here the sample value is 2. So when we will compare 2 with 0 and 1, the maximum value will be equal to 1. So at plus 1 index the answer will be equal to 2. Similarly, at minus 2 index, here the sample value is 2, and here the sample value is 3, and here the sample value is 1. So when we will compare 1 with 3 and 2, the maximum value will be equal to 3. So at minus 2 index, the answer will be equal to 3. So the thing to remember is that if you are going to add the sample values, or if you are going to compare the values, or if you are going to apply any operation, the required operation will be performed at the respective index values. This is the key point which you should remember while performing operations between various discrete signals. Now let's try to understand how we can calculate the output of an accumulator. Before calculating the output, first try to understand what is the meaning of this difference equation. To calculate the sample values of y of n, or to calculate the output of an accumulator, what we have to do, we have to collect the sample values of x of n from minus infinity to the current index value and then producing their summation. For example, if we want to calculate y of 3, then it means we have to collect the sample values of x of n from minus infinity to the plus 3 index, and after collecting all those values we will add them in order to calculate a single output value of y of 3. So this difference equation can also be written as x of n plus x of n minus 1 plus x of n minus 2 and so on. So this is our x of n, which is the bounded signal or defined from minus 3 to plus 3. So before minus 3 index up to minus infinity index you will find all zeros. Now let's start computing the output or the values of y of n. To calculate the output corresponding to minus 3 index, what we have to do, we have to add the sample values of x of n from minus infinity to the minus 3 index. So when we will add 3 with all these zeros, the answer will be equal to simply 3 for minus 3 index. So here, as you can see, the answer of y of n is equal to 3 at minus 3 index, and obviously the value of y of n at minus 4 index will be 0, because when all these zeros will be added together we will get the 0. Now in order to compute the output corresponding to minus 2 index, what we have to do, we have to add all these numbers. So when all these infinite zeros will be added in 3 plus 2, the answer will be equal to 5. So here we will get the 5 corresponding to minus 2 index. Similarly, you can compute all the remaining values. For example, we are going to calculate the sample value corresponding to 2 index. So what we have to do, we have to add all the sample values of x of n from minus infinity up to the current index value. So 3 plus 2 is 5, 5 plus 1 is 6, 6 plus 0 is 6, 6 plus 1 is 7, and 7 plus 2 is 9. So you will get the result 9 corresponding to 2 index. Similarly, for 3 index, 9 plus 3 will be equal to 12. And if you will compute the output of an accumulator after the 3 index values, the result will be equal to 12. Because when all these sample values will be added together, the answer will remain 12. So this was the first approach or the first method for calculating the output of an accumulator. There is another possible way to calculate the output of an accumulator which is more efficient than this one. So let's see how we can do it. So in this method we can calculate the output of an accumulator by just adding two values, which are the current input sample value and the previous output sample value. So let's start with the minus 3 index value. To calculate the output at minus 3 index, the answer will be simply equal to 3, because before 3 there are all zeros. Now for minus 2 index we have to add two values, the current input value which is 2 and the previous output value which was 3. So 3 plus 2 will be equal to 5 at minus 2 index. Now for minus 1 index the current input value is 1 while the previous output value was 5, which was the summation of these two samples. So 5 plus 1 is 6 at minus 1 index. Similarly, for 0 index, 6 plus 0 will be 6. Then at plus 1 index, 6 plus 1 will be 7. Then 7 plus 2 will be 9. Then 9 plus 3 will be 12. And then 12 plus 0 will be 12. And 12 plus 0 will be 12. So this is how we can calculate the output of an accumulator, and in this case the difference equation can be written like this. y of n is equal to x of n, which is the current input sample value, and the previous output value can be written as y of n minus 1. So this y of n minus 1 is actually a 1 unit delayed version of y of n. And the working of this difference equation can be explained with the help of this block diagram. As you can see, to calculate every sample value of y of n, we have to add two samples. So this is an adder block which is adding two sample values. The first sample or the first input to this adder is x of n, which is representing the current input sample value, while the second input to this adder is y n minus 1, which is so called the previous output value. Now, how we can obtain the previous output value? With the help of current output value produced by our system, we have to pass every current output sample value through a unit delay element in order to get the y of n minus 1. So every current output value will be feedback to our system so that we can add y of n minus 1 with x of n in order to get the result of y of n. And one more thing which you can observe here, this delay element basically represents the memory element, or in other words, we have to store every current output value in our computer memory, or this memory element is basically storing or holding every current output sample value, and it is producing its output after every unit delay element or after every sampling interval. So this unit delay element is also representing the memory element whose task is to hold the current output sample value so that we can use them in the next iteration for addition purpose. So in this system, which is y of n is equal to x of n plus y of n minus 1, we have implemented an accumulator, and the order of this system is 1 because the maximum amount of shift in this equation is 1. So this is the first order accumulator where we have used feedback in this implementation. Now let's summarize the discussion on the difference between real-time processing and post-processing. As we discussed earlier, real-time processing performs operation on the real-time data. And in real-time data, we cannot access the future samples of signal. We can use only the present and the previous samples of our signal. But the condition is that in order to access the previous values of our signal, we must have to store them on our computer memory. In only that case, we can access the previous values, otherwise not. While in the case of post-processing systems, as we have to process the recorded data, which means that all the sample values of the signal are available because data has already been recorded and stored on our computer memory. So in post-processing, we are allowed to use all samples of our signal, including present, previous, and the future samples of our signal. Now let's consider this example. These are the same 6 different discrete time systems for which we have calculated y of n for a given x of n. Now, in this example, we have to identify which system can support real-time processing and which system can process only the recorded data. So your task is to just identify which systems can process real-time processing and which systems cannot process our signal in real time. And it is very easy to find. You have to just observe whether the current output value of our system is depending upon the future samples of input or not. So if the current output of a system is depending on the future samples of input, then such systems cannot support real-time data. So as you can see in the third, fourth and fifth system, current output value is depending on the future samples of our input. So these three systems cannot handle our signal in real time. They can entertain only the recorded data because for the calculation of y of 3 we will need x of 4. For the calculation of y of 5 we will need x of 6. So it can happen only when the data has already been recorded. While in the case of real-time processing systems, if the current output value is just depending on the current samples of input or the previous samples of our input, So those systems can handle our signal in real time because there is no need to access the future samples of our input. So that's it for this lecture. In the next lecture, we will discuss some important properties of the discrete time systems. Until then, thank you very much and Allah Hafiz.